It's really a great opportunity to tell you about this. The BAS survey is the result of about 50 researchers working together, many of them from Chile, and we've got some exciting results. So I'll talk to you about our second data release and introduce you to the BAS survey, and then talk to you a little bit about what we're learning in terms of molecular gas and black hole growth in the local universe. So thanks again for the opportunity to talk. So to give you an overview of what the BAS survey is, it's basically taking observations from Swift-BAT over the last 15 years and stacking them on the whole sky to get a deep, sensitive hard X-ray survey. And so we're tracing things in the 14 to 200 keV range. We have about 1,100 AGN. And the figure shown here is basically the whole sky. And so you can see the red dots are the AGN, and the galactic plane in blue is galactic sources. So I'm going to be focusing on the AGN. The nice thing about the 14 to 200 keV X-ray range is it's really tracing AGN activity, the total bolometric luminosity. It's not affected by star formation, obscuration up to really Compton thick levels. And so we get a nice sample of unobscured and obscured AGN with bolometric luminosity. So one of the big motivations for the BAS survey is this sample is really a benchmark for high redshift X-ray selected AGN at the peak of black hole growth at redshift 1 to 2. So we're looking at the whole sky, so we get the most luminous sources. And this is a plot of the X-ray luminosity in 2 to 10 keV versus the redshift. So the purple stars are the BAS survey sources. And you can see going out to about redshift 0.3, there we're finding all of the most luminous AGN. And so when you look at the comparison to redshift 1 to 2, to many of the surveys, we have sort of similar luminosities, 10 to 43, 10 to the 44 as these surveys. So we can study luminous black hole growth at low redshift. And at low redshift, we can get really high spatial resolutions. And we can also get really high sensitivities across a full range of wavelengths. And we can do things like measure velocity dispersions, which are hard to do at higher redshift. So to give you an overview of what we're trying to do in BAS is really get the full multi-wavelength picture of black hole growth. So I'll tell you about the optical spectra and our second data release. And so we're getting high spectral resolution, so we can get velocity dispersions and also measure all the emission lines. And so we in the second data release, we really have 95% of black hole mass measurements using velocity dispersions or broad H alpha or broad H beta. And combined with this, we have, basically the best X-ray spectra for AGN. We have coverage with Swift, with BAT, with hundreds of sources with NuStar, with XMM, Chandra. And right now we also have an ongoing HST program in the UV. So we really want to understand the bolometric luminosity. And we have a large optical program that's been done with HST and near infrared. And we also have a large near infrared spectra program being done now, almost 500 AGN before the launch of JWST. So that's great. And near infrared spectra. And I'll talk to you a little bit more about some of the molecular gas work later. So the survey's been going for a few years, and we've just finished our 20th paper, which is great. So I just wanted to, I'm not going to talk about all of these, but I just wanted to, give you kind of a list of some of the different topics we're doing. And the column on the right is the special issue. We're going to do a special issue in the Astrophysical Journal, and this is releasing the 1500 optical spectra from the DR2 and 400 near infrared spectra. And so I'll give you just some of the high level results from that and tell you a little bit more about that. So this next plot here is showing where our spectra for the second data release are coming from. So in the south, this is mainly from VLT Xshooter, which is great. So we can get high spectral resolutions from the optical to the near infrared. In the north, it's mainly from Palomar. So we're getting, 3,200 angstroms to 10,000 angstroms. So we got a really wide spectral coverage. So what we can do with that, these are nearby galaxies, so we can get really good measurements of velocity dispersions. So this is showing you one of the sources, and you can see that we can fit a number of absorption lines, calcium, magnesium, and get independent estimates of velocity dispersions. So basically with these measurements along with broad lines for the unobscured sources, we can get black hole mass measurements in about 95% of the sources. So, we do have a fraction of sources that a small number that, are, in the galactic plane or in some other places that are difficult to measure. But basically we're getting almost the whole sample, which is great. So we can understand how black hole growth and high Eddington ratio sources, how they're linked to the host galaxies. So the other thing about this survey is this is really high spectral resolution. So, R of 5,000, so a factor of 2 more than like the Sloan Digital Sky Survey. So some interesting things come out of that. This plot here is showing, so basically we're uncovering some of these low mass black holes, even though they're in luminous AGN and sometimes in, somewhat larger stellar mass galaxies. And so the plot on the left is showing a low mass black hole with a very low velocity dispersion of 39 kilometers a second. And the plot on the right is sort of showing you how that would be basically in sort of the very low mass black hole mass in terms of its velocity dispersion. So we find these sources because we have this large systematic survey of hundreds of sources. And we're really, with this source on the left, we re-observed it again with even higher spectral resolution. So we'll have good measurements for all of the sources. So this is another highlight. So this is a DR2 paper, part of our Spectra release. It's already been submitted, looking at the near-infrared spectra from Xshooter. So this shows, one particular source where I think you can see the importance of spectral resolution and also of the wide wavelength coverage. So this is actually a double peak source. A lot of times that's associated with outflows. In rare cases, maybe with binary AGN or a double AGN. And so you see with hbeta, there's two peaks that are barely resolved. You wouldn't find this in the Sloan Digital Sky Survey because they wouldn't have a high enough resolution. And then if you go to the infrared and you look at Passion alpha, where there's a factor of 5 to 10 less extinction, you see this hidden broadline source. So we're really uncovering a lot of interesting things with this wide wavelength coverage. So now some of the results. So the great thing about joint, X-ray, and optical is you can uncover some really interesting trends with obscuration in sources with broad H alpha. And we talked yesterday in this conference a lot about what are the best ways to sort of measure black hole mass. One of the interesting things that we found is that you have to be careful about H alpha. You might assume that it's less affected by obscuration, which is true, but looking at our sample, if you do a plot of the X-ray obscuration, the NH, which is shown on the left, and you look at the broad H alpha versus the X-ray luminosity, which should be basically constant, because they're both tracing black hole growth, you find that as you go to higher NH, so above about 10 to the 21, it really starts to drop off. So you're going to underestimate the mass of the black hole. Basically, we have to be careful of Seyfert 1.9s because we have some X-ray obscuration. And so, you can get around this with the near-infrared spectra. You can get around it with measurements of the NH, so that giving you an idea of whether you're underestimating the broad H alpha. And some of the other results we have are sort of emission line measurements. And you find that most of the sources, most of the bad AGN are in the Seyfert galaxies, but basically a third, are in liners or in composites. They have weak or no emission lines. So really are tracing a unique population. The other interesting thing is that we find a lot of sources with high N2H alpha, which we think is associated with high Eddington ratios. This is work done by QSOC-O. And then we find that most of the optical obscuration in terms of, if it's a Seyfert 1 with broad hbeta, it's going to be X-ray unobscured. And most of the Seyfert 2s are going to be X-ray obscured. So the plot on the bottom is showing the H alpha full width half max versus the NH. And if you just look at the blue sources, so these are Seyfert 2s, the H alpha full width half max is a few hundred kilometers a second. Most of those have high X-ray obscuration above 10 to the 22. And the same is true if you look at Seyfert 1s. Most of them, it's a little bit hard to see because many of them are at no X-ray obscuration, but most of them have NH less than 10 to the 22. Some of the outliers are actually interesting sources. Some of them are changing look AGN. Some of them have complex obscuration. So we're looking at those. That's an exciting, interesting population. So just the final thing from the BAS DR2 is, so we have 95% of the black hole masses. So we can really, for the first time, put together the full black hole mass distribution and Eddington ratio distribution for a sample of obscured and unobscured AGN using velocity dispersions and single epoch measurements. So this is work done by Tonima Anana. She's going to be talking tomorrow, and we'll maybe give you a little bit more about this, but just to show you two plots, the black hole mass function on the left column and the Eddington ratio distribution function on the right column. And so we do find that the type 1 AGN tend to have higher Eddington ratios. And you can sort of see that if you look at the plot on the right and, say, look at 10 to the -1, and you can see that the overall density is much higher in the type 1s. So this is consistent with actually a really nice result by Claudia Ricci from Nature from a couple years ago, showing that the high Eddington ratio sources might actually be able to blow out some of the dusty gas. So that's really nice work by Tonima. So for the second part, I wanted to really switch to black hole growth in the molecular gas in the local universe. I think we found a lot of interesting trends. And so the survey that we've been doing is looking at the total host galaxy molecular gas. So the nice thing about the BAT sample is it's basically just selected on AGN properties. And in the past, people have looked at, IR selected AGN, where you might have some bias towards star formation. But we now can look at a large sample just on its AGN properties and say, what is the molecular gas and how is it different from inactive galaxies? So this is showing you the first 214. This was recently published a few weeks ago, and you can find it on arXiv. There's also other surveys being done with IRAM that Taro Shimizu is doing. And we have another approved program with Apex to do some deeper observations. So this is a typical galaxy. The apex beam is on the left, and the image of the galaxy. So the dashed line in the orange is showing you that we're getting most of the host galaxy molecular gas. The plot on the right is showing you the CO 2:1 spectra. And actually, surprisingly, most of our sample is detections, which was a really interesting result because we didn't actually expect that. So the next part, I'm going to talk a little bit about how the BAT AGN are different from inactive galaxies. So there's a really large survey called X-Cold Gas, which looked at 500 galaxies with IRAM. And basically, we took the higher stellar mass galaxies, which is a nice control sample to understand how black hole growth works compared to our AGN sample. So they're in the same range of stellar masses. So what we found, that one of the main results is that AGN tend to avoid passive or quenched galaxy hosts. So they have this constant gas fraction with stellar mass. So the plot on the left is showing you both samples. You can see blue is the AGN galaxies. Upper limits are shown with the arrows. Red is the inactive galaxies. And the plot on the right is showing you that 10.4 in terms of the log of stellar mass, they're similar. But when you get to higher stellar masses, you see this large difference. So AGN tend to avoid galaxies with very low gas fractions or molecular gas.
4 minutes, Mike. Yeah.
Okay. So galaxies with more molecular gas are likely to host AGN, but not all galaxies are going to host powerful Seyferts. So the plot on the left is showing you the molecular gas mass function. So cold gas is basically sampling all of the galaxies. And with our AGN sample, this is a sky survey. So this is sources above 10 to the 44 in bolometric luminosity. And so you can see it's basically flat compared to in the blue points, compared to the red points. And if you take the number of AGN divided by the number of galaxies, which is the plot on the right, this gives you the probability of hosting an AGN. So the interesting thing that you find is that the probability goes up by a factor of 10 to 100 as you get to higher molecular gas masses. But at the highest molecular gas masses, not everything hosts a powerful AGN. So that I think is really interesting. But the fact that we're finding a factor of 10 to 100 more at high molecular gas mass is telling you something about where AGN activity happens. So the difference in molecular gas is actually also most pronounced in sort of the early elliptical morphologies. So the plot on the left is showing the morphologies of the two samples and their detection fraction. The plot on the right is showing you the gas fractions of the ellipticals. So basically, if you're an elliptical inactive galaxy, you're almost never detected in molecular gas. But with our AGN sample, we find a lot of these bulge-dominated sources having significant molecular gas. So it really tells you that you probably need some fraction of molecular gas to host an AGN typically. So we also find a weak but significant trend with Eddington ratio. So there's significant variations. We're also looking at the total host galaxy molecular gas. So in the future, we could presumably look with ALMA. And so there's probably a lot of stochastic variability happening, but there still is a significant trend that we can look at with larger samples. And so we don't really find any evidence of AGN feedback. The plot on the left is showing you the distribution compared to the main sequence of star formation. So the blue is the AGN galaxies. Most swift AGN are on the main sequence, but in inactive galaxies, you have this fraction at 10 to the -1 or 10 to the -2 that sort of don't have much star formation. But if you look at the depletion time, which is essentially the star formation, how fast the star formation would deplete the molecular gas, you find that the samples are very similar. So we don't see that higher Eddington ratio or higher X-ray luminosity AGN are actually depleting the molecular gas and affecting the total overall gas supply. So here's the summary. So BASS is really combining a detailed optical, infrared, molecular, and X-ray spectral analysis. Our DR2 has a lot of really exciting papers, and it's going to be released in the spring with the catalogs and the science results. In our molecular gas study, AGN tend to like to live in gas-rich galaxies, and they really avoid passive galaxies. And the trend is largest in these elliptical or early types. And there's a weak with significant trend with Eddington ratio and molecular gas. So I think in terms of black hole growth in the local universe, what the link we're seeing may help explain some of these correlations between black hole mass and the bulge, and possibly between some of the redshift evolution we see of star formation and black hole growth. So if you're interested in BASS, please contact us. We'd love to work with you if you have a scientific idea. So thank you so much.